Hello friends, welcome to my lecture on meromorphic functions. An analytic function whose only singularities in the finite complex plane are poles is called a meromorphic function. For example, we can consider rational functions with a non-constant denominator. You know that a rational function is a quotient of two polynomials. Say suppose fz is a rational function, then we can write fz equal to pz over qz, and the zeros of qz are then the polynomials, zeros of qz are then the poles of fz. So, we can easily prove that if qz has a 0 of order m at z equal to z naught, then we can write qz as z minus z naught to the power m into some function phi z, where phi z naught is not equal to 0 and phi z is analytic in some small neighborhood of z naught. So, then putting the value of qz, we shall have fz equal to bz divided by z minus z naught to the power m into phi z. Now, pz over phi z is an analytic function at z naught. So, we can write this as 1 over z minus z naught to the power m into since pz over phi z is analytic at z equal to z naught, we can expand it by the Taylor series and then write sigma n equal to 0 to infinity say a n z minus z naught to the power n. Okay, where you know that where a n is equal to nth derivative of pz over phi z at z equal to z naught. Okay. Now, this is equal to, if you write this, expand this series, then you can see a naught z minus z naught to the power 0. So, we shall have 1 upon z a naught upon z minus z naught to the power m, then a 1 z minus z naught to the power m minus 1 and so on. When your n will be equal to m, then we will have a m and then you will have a m plus 1 z minus z naught and so on. Okay. Now, we can see here that a naught is not equal to 0 because p z naught over phi z naught is not equal to 0. P z naught over phi z, p z over phi z is equal to sigma n equal to 0 to infinity a n z minus z naught to the power n. So, p z naught over phi z naught is equal to a naught. Okay. Now, p z naught over phi z naught is not equal to 0. So, this implies that a naught is not equal to 0. Okay. So, this means that now this is Laurent series of the function f z. Okay. So, since a naught is not equal to 0, f z has a pole of order m at z equal to z naught. So, if q z has a 0 of order m at z equal to z naught, then f z has a pole of order m at z equal to z naught. Similarly, tan z we know is equal to sin z over cos z. So, the zeros of cos z become the poles of tan z, and cot z is cos z over sin z, the zeros of sin z, at the zeros of sin z we have the poles of cot z. Similarly, sec z is 1 over cos z, the zeros of cos z give us the poles of sec z, and cosec z is 1 over sin z, the zeros of sin z give us the poles of f z. So, they are give us the poles of cosec z. So, so rational functions with a non-constant denominator, tan z, cot z, sec z, cosec z, they are all examples of meromorphic functions. Now, let us look at a very useful result on meromorphic functions. It is regarding poles and zeros of a meromorphic function. If f z is analytic inside and on a closed contour C, except at a finite number of poles inside C, then by using Cauchy's residue theorem we can determine the number of zeros of Fz inside C. Let us see how we do that. Suppose Fz is analytic inside and on a closed contour C except at a finite number of poles inside C and does not vanish on C. Okay. You can see here this formula 1 over 2 pi I integral over C f prime z over Fz equal to n minus p. So, here your Fz cannot be 0 on C. If Fz takes value 0 on C, then integral over C f prime z over Fz will not be defined. So, then here n is the number of zeros of Fz inside C and p is the number of poles of Fz inside C. Both zeros and poles are being counted according to the order of their multiplicity. Now, suppose that, so let us prove this, suppose that Fz has a 0 of order m at z equal to a, then in a certain neighborhood of z equal to a, say mod of z minus a equal less than r, we can write Fz as z minus a to the power m into gz, mod of z minus a less than r, where gz is an analytic function in the neighborhood mod of z minus a less than r and gz does not become 0 at z equal to a, that is Ga is non-zero. So, since gz is analytic in this neighborhood, it is continuous in this neighborhood. Okay. So, Ga not equal to 0 implies that we can get a sufficiently small neighborhood of a z equal to a in which gz is not 0 throughout the neighborhood. So, mod of z minus a less than r, we can take the neighborhood where gz is not equal to 0 throughout the neighborhood. This r will be can be taken sufficiently small. Now, from here it follows that if you take ln both sides, this equation gives you ln Fz equal to m times ln z minus a plus ln gz. Now, differentiating with respect to z, what do we get? 1 over Fz into f prime z equal to m over z minus a plus g prime z over gz, that is we get this equation. So, now g prime z over gz is analytic in mod of z minus a less than r, because gz is not 0 throughout this neighborhood, mod of z minus a less than r and gz is analytic. So, g prime z over gz is analytic in this neighborhood and hence f prime z over Fz has a, so what we can do, since g prime z over gz is analytic in mod of z minus a less than r, okay, we can expand g prime z over gz by a Taylor series. So, actually this is nothing but m over z minus a plus sigma n equal to 0 to infinity a n z minus a to the power n. Okay. Where ans are again where ans are dn over dzn g prime z over gz at z equal to a divided by n factorial. So, you can take n factorial here also. Here when I did this I wrote a n equal to this. So, here also we can write a n z minus z naught to the power n by n factorial. So, what we can do now f prime z over f z is, now this is nothing but the Laurent series of f prime z over f z, and the principal part of f prime z over f z contains only the term in negative powers of z minus a m over z minus a. Okay. The coefficient of 1 over z minus a gives the residue of f prime z over f z. So, we can say that residue of f prime z over f z at z equal to a, which is a simple pole of f prime z over f z, is equal to m. Okay. So, f prime z over f z has a simple pole at z equal to a with residue m. Now, m was the order of the 0, okay, of f z, and we have seen that f prime z over f z has a pole at z equal to a with residue m. So, we can say that the sum of residues of f prime z at the zeros of f z is equal to n. If you recall, n is the number of zeros of f z. where the zeros are being counted in order according to their order of their multiplicity. So, here the 0 at z equal to a occurs m times. So, it will be counted as m zeros at z equal to a, and at z equal to a we get a pole of f prime z over f z with residue m. So, we can say that the residue of f prime z, sum of residues of f prime z over f z at the zeros of f z is equal to n. Now, if z equal to b is a pole of order n of the function f z, then in a certain neighborhood say 0 less than mod of z minus b less than r dash of z equal to b, we can write f z equal to h z over z minus b to the power n. Here is the proof. You can say that z equal to b is a pole of order n of the function f z. So, f z can be written as sigma s equal to 0 to infinity b s z minus b to the power s m equal to sigma m equal to 1 to n c m over z minus b to the power m, 0 less than mod of z minus b less than r dash. Now, this can be further written as f z equal to, we can write 1 over z minus b to the power n outside, then inside the bracket we shall have sigma s equal to 0 to infinity b s z minus b to the power s plus n, then we will have c 1 times z minus b to the power n minus 1, c 2 times z minus b to the power n minus 2 plus and so on, plus c n minus 1 z minus b plus c n. Now, at z equal to b, this expression inside the bracket gives c n, and c n is not equal to 0 because f z has a pole of order n at z equal to b. So, we can write this expression inside the curly bracket as h z, then we shall have f z equal to h z over z minus b to the power n, and this h z is a analytic function because it is represented by a power series. So, h z is represented by a power series, therefore, it is an analytic function, and also that h b is not equal to 0. So, h z equal to h z f z equal to h z over z minus b to the power n, where h z is analytic and non-zero. So, we can take this r dash to be so small that inside the region mod of z minus b less than r dash, h z is not equal to 0 throughout, because h z is analytic and h b is not equal to 0. So, we can find a small neighborhood of z equal to b in which h z is not equal to 0 throughout. So, let us take r dash to be so small that it is not 0 throughout this disk mod of z minus b less than r dash, and then we take logarithm of this, and logarithm as in the case of the 0 at z equal to a. Okay. Here also we can see that after taking logarithm both sides and differentiating with respect to z, we shall arrive at this expression. So, you can see ln f z is equal to ln h z minus n times ln z minus b. Then we differentiate with respect to z. So, 1 over f z into f prime z equal to h dash z over h z minus n over z minus b. Okay. Now, h prime z over h z is an analytic function in this neighborhood mod of z minus b less than r dash and not equal to 0 throughout this neighborhood, h z is not equal to 0 throughout this neighborhood. So, h prime z over h z can be expanded in a Taylor series, and we shall write f prime z over f z equal to sigma n equal to 0 to infinity, okay, some constants a n into z minus b to the power n divided by, I think we should write here m equal to 0 to infinity, z minus b to the power m divided by m factorial and minus n over z minus b. So, where a m is equal to d m over d z m h prime z over h z at z equal to b. Okay. So, this series is now the Laurent series of f prime z over f z, and this part is the principal part of f prime z over f z. Okay. So, so here we can say that f prime z over f z has a pole, simple pole at z equal to b, and the residue of f prime z over f z at z equal to b is equal to minus n. Okay. And you can see that n is the order of the pole, okay, n is the order of the pole at z equal to b. Okay. So, f prime z over f z has a pole at z equal to b with residue minus b. Okay. And so, we can say that this minus p denotes the so p is the, here p is the number of poles, and therefore, we can say that and they are counted according to their multiplicity. Okay. So, we can say that this minus p is the so sum of the residues of at the sum of the residues at the poles of f f prime z over f z, sum of the residues at the poles of f z is minus p, okay, because f z had a pole at z equal to b, okay, of order n. So, sum of the residues at the poles of f z is minus p, and therefore, by Cauchy residue theorem, what do we say? 1 over 2 pi I integral over c f prime z over f z is sum of the residues at the poles of f prime z over f z inside C. Okay. So, this is equal to n minus p. This proves the theorem. So, let us now go to argument principle which depends on this previous theorem. So, if f z is analytic inside and on a closed contour C and f z does not vanish on the curve C, then n is equal to 1 over 2 pi delta C argument of f z, where n is the number of zeros of f z inside C counted according to the multiplicity, and delta C argument of f z denotes the variation of argument of f z around C. So, let us prove this. Since f z is analytic inside C, okay, we have this here, we are given that f z is analytic inside and on C. So, since f z is analytic inside C, by the preceding theorem 1 over 2 pi integral over C f prime z over f z dz will be equal to 0, because f z does not have any singularities inside C. So, p which is p will be equal to 0. So, this is equal to n, and now d over dz log of f z, okay, d over dz log of f z equal to, now here you can see f z we are assuming that f z is not equal to 0 on C. Okay. We are assuming that f z is not equal to 0 on C. So, we can take log of f z. Okay. So, let us consider d over dz of log of f z. This is f prime z over f z, and so what we can say here, if you integrate this equation, then integral over C f prime z over f z will be equal to variation of log f z round the curve C, okay, where delta C denote the variation round the curve C. Now, log of f z is equal to log of mod of f z plus I times argument of f z. Now, we know that log of mod of f z is a single valued function, and therefore, from this equation from 3 and 4, what do we notice? Delta C log of f z will be equal to I times delta C of argument of f z, because log mod of f z is single valued. So, it does not change round C. So, what we have, this will be equal, n will be equal to 1 upon 2 pi I integral over C f prime z over f z, and this will be equal to 1 upon 2 pi I delta C log of f z, and therefore, delta C log of f z is equal to I times delta C argument of f z. So, we shall have 1 over 2 pi delta C argument of f z. So, n is equal to 1 over 2 pi delta C argument of f z. Now, let us look at the Rouse's theorem. Rouse's theorem we can use to determine the number of zeros of f z, the given function f z inside C. So, if f z and g z are analytic inside and on a closed contour C, and mod of f z is less than mod of g z on C, then Fz and Fz plus Gz have the same number of zeros inside C. This is the theorem. So, here you can see that mod of Gz is the absolute value of Gz. So, it is always greater than or equal to 0. Therefore, from the condition mod of Fz less than mod of Gz, it follows that mod of Fz is always strictly greater than 0, and therefore, Fz cannot vanish on the curve C. Okay. So, now let us also show that Fz plus Gz also cannot be 0 on C. This we can easily show here. Suppose for some z on C, Fz plus Gz is equal to 0, then at that point, okay, then at that point Fz will be equal to minus Gz, and so mod of Fz will be equal to mod of Gz, but we are given that mod of Fz is less than mod of Gz. Therefore, Fz plus Gz cannot be 0 at any point on the curve C. Okay. Now, so Fz cannot be 0 on the curve C, and Fz plus Gz cannot be 0 on C. Now, let us consider that let us say that n and n dash denote the number of zeros of Fz and Fz plus Gz inside C respectively. Then by the argument principle, by the theorem which we proved just now, we will have 2 pi n delta C argument of F, okay, because n denotes the number of zeros of Fz inside C. So, by the previous theorem 2 pi n equal to delta C argument of Fz, and n dash denote the number of zeros of Fz plus Gz inside C. So, 2 pi n dash will be equal to delta C argument of F plus G. Now, we know that argument of two complex numbers Z1 into Z2 is equal to argument of Z1 plus argument of Z2. Okay. So, by that argument of F plus G can be written as argument of Fz, this Fz plus Gz. Okay. So, argument of Fz into 1 plus Gz divided by Fz. So, using this result we have argument of Fz plus argument of 1 plus Gz by Fz. Okay. So, argument of delta C argument of F plus G will be equal to delta C argument of Fz plus delta C argument of 1 plus Gz by Fz. Now, delta C argument of F is equal to 2 pi n. So, we can put the value here, and then we shall have from this equation 2 pi n dash minus n is equal to delta C argument of 1 plus G by F. Now, let us recall that we are given that mod of Gz is less than mod of Fz on C, and therefore, the point W equal to 1 plus G by F always lies in the interior of the circle mod of W minus 1 equal to 1 as Z moves on C. So, how does that happen? We can consider this 1 plus G by F 1 plus Gz by Fz we are writing as Wz. Okay. So, W is equal to, this gives you W minus 1 mod equal to mod of Gz by Fz. Okay. Mod of W minus 1 equal to mod of Gz over mod of Fz, and mod of Gz over mod of Fz is less than 1. So, mod of Gz over mod of Fz is less than 1. So, we get mod of W minus 1 less than 1 for all Z belonging to C. So, as Z moves on C, okay, W lies, this W lies in the interior of the circle mod of W minus 1 equal to 1. Thus, if you take W to be, so let us draw this circle, this is 1 in W plane, and we have this circle, this mod of W minus 1 equal to 1. So, thus if you take W to be rho ei phi, take W to be rho ei phi, this is W, let us say, okay, W equal to rho ei phi. So, the argument of W is equal to phi, and rho is its distance from the origin. Okay. So, thus if W equal to rho e phi, the argument phi, now you can see that the argument of W varies between minus pi by 2 to n pi by 2. This is minus pi by 2 and here argument is pi by 2. Argument of w here is minus pi by 2, here it is pi by 2. So, argument of w lies between minus pi by 2 and plus pi by 2, and therefore, argument of 1 plus g by f which is equal to phi, because this we are denoting 1 plus g by f we are denoting by w. So, argument of w is phi. Okay. It returns to its original value as z describes C. Okay. You can see anywhere you take, okay, the argument, if you go from any point this, okay, and come back to this point, the argument will always be the same. So, the argument phi always lies between minus pi by 2 and pi by 2, hence argument of 1 plus g by f, that is argument of w which is equal to phi, returns to its original value as z describes C. Okay. You are moving from here to here. Okay. So, when you come back to the original point, the argument will return to its original value. So, thus delta C argument of 1 plus g by f, there is no change in the argument of 1 plus g by f as z varies around C. So, it is equal to 0, and therefore, n is equal to n dash. Now, let us show that every polynomial of degree n has n zeros. Suppose we take the polynomial p z equal to a naught plus a 1 z plus a 2 z square and so on a n z to the power n, where a n is not equal to 0. This be any polynomial of degree n. Okay. So, let us define f z to be equal to a n z to the power n. Okay. This is f z we are taking, and g z we take as a naught plus a 1 z plus a 2 z square and so on a n minus 1 z to the power n minus 1. Then you can see from the definition of f z equal to a n z to the power n gives you, if you put it equal to 0, it gives you n zeros at z equal to 0, since a n is non-zero. So, f z has n zeros at the origin because a n is non-zero, and let us take C to be the circle mod z equal to r, where r is greater than 1. Let us take a circle mod z equal to r, and let us take r to be greater than 1. Then on the circle C, mod of f z is equal to mod of f z is equal to mod of a n z to the power n, which is equal to mod of a n into mod of z to the power n. So, mod of z equal to r on C. So, mod of a n r to the power n on C. Okay. Now, mod of g z will be what? Mod of g z by triangle inequality is less than or equal to mod of a naught. Mod of g z is less than or equal to mod of a naught plus mod of a 1 mod of z mod of a 2 mod of z square and so on mod of a n minus 1 into mod of z to the power n minus 1. So, this is mod of a naught plus mod of a 1 into r mod of a 2 r square and so on mod of a n minus 1 r to the power n minus 1. Okay. So, we will get this. Now, mod of g z is less than mod of f z. Okay. So, what we will get? This quantity will be less than this one. Okay. And therefore, what we can do, r will be greater than. So, using mod of g z less than mod of f z and these estimates of mod of g z and mod of f z here, we arrive at r greater than mod of a naught plus mod of a 1 plus mod of a 2 mod of a n minus 1 over mod of a n. Okay. So, if r is sufficiently large, okay, here you can see that while writing this inequality, okay, I have used the fact that r is greater than 1. When r is greater than 1, r square will be greater than r cube will be greater than r, okay, r to the power r square when r is greater than 1, then we can write r is less than r equal to r n minus 1, r 2 is less than r equal to r n minus 1, and r n minus 1 is less than or equal to r n minus 1. So, here r square r to the power n minus 2 all can be replaced with r to the power n minus 1. So, here we are using r greater than 1. Okay. Now, with this estimate and the estimate of mod of f z, we arrive at r greater than this. Okay. So, if you take r to be greater than 1 and also greater than this value, okay, then by Raoult theorem P z equal to f z plus g z, okay, has the same number of zeros inside mod of z equal to r as f z, and f z has zeros n zeros at z equal to 0. Okay. So, P z also has n zeros inside mod of z equal to r. You can see that z equal to 0 inside z equal to 0 lies inside mod of z equal to r. It is the center of mod of z equal to r. So, mod of f z and so f z and f z plus g z have same number of zeros inside C. Now, let us consider the equation z to the power 8 minus 4 z to the power 5 plus z square minus 1 equal to 0. We will show that the zeros of this polynomial of degree 8 in z, there are 8 roots of this polynomial. Those 8 zeros of this equation are the polynomial, they lie inside mod of z equal to 1. Okay. So, what we will do, let us take f z equal to minus 4 z to the power 5 and g z equal to z to the power 8 plus z square minus 1. Okay. Then we can see that then mod of f z is equal to 4 times mod of z to the power 5, okay, which is equal to 4 on the curve mod of z equal to 1. Okay. And mod of g z, we see that mod of g z is less than or equal to mod of z to the power 8 plus mod of z square plus 1 by triangle inequality. Okay. So, this is equal to 1 plus 1 plus 1. So, 3 on mod of z equal to 1. Okay. So, we have mod of g z is less than mod of f z for all z belonging to the curve C. Okay. And thus, by Raoult theorem, f z and f z plus g z have the same number of zeros. Okay, inside C. Okay, now let us notice that f z is equal to minus 4 z to the power 5. So, f z has a 0 of order 5 at z equal to 0. And therefore, therefore, f z plus g z also has 5 zeros inside mod z equal to 1. So, this z equal to 0 lies inside, which lies inside C, and hence f z plus g z, which is equal to z to the power 8 minus 4 z to the power 5 plus z square minus 1 also has 5 zeros. So, thus f z plus g z also has 5 zeros inside mod z equal to 1. So, this means that the other 3 zeros, there are 8 zeros of this polynomial, the other 3 zeros lie outside mod z equal to 1. Okay. Now, let us go to next question. Suppose we have the equation z to the power 4 plus 6 z plus 1 equal to 0, then let us find first where all the roots of this equation lie. We see that all the 4 roots of this equation lie inside mod z equal to 2, but if you consider the circle mod z equal to 3 by 2, only one root lies inside mod z equal to 3 by 2. So, let us take let f z be equal to 6 z plus 1 Okay. Let fz be equal to 6z plus 1 and gz be equal to z to the power 4. Okay. Then we see that mod of fz is less than or equal to 6 times mod of z plus 1. Okay. So, this is 6 times 2 plus 1, okay, which is equal to 13, and mod of gz is equal to mod of z to the power 4, which is equal to 2 to the power 4. So, we shall have 16. So, mod of fz is less than mod of gz, okay, for all z on mod z equal to 2, and therefore, gz and fz plus gz must have same zeros, same number of zeros inside mod z equal to 2. Now, let us look at the zeros of gz. Gz equal to z to the power 4 implies that gz has a 0 of order 4 at z equal to 0. Okay. So, fz plus gz, and this of which lies inside mod z equal to 2. Okay. So, gz has a 0 of order 4 at z equal to 0, and z equal to 0 lies inside mod z equal to 2. So, gz has 0 of order 4 inside mod z equal to 2, and therefore, fz plus gz, which is equal to fz plus gz equal to z to the power 4 plus 6 z plus 1 also has 4 zeros inside mod z equal to 2. Now, this is a fourth order equation, this is the fourth order polynomial equation. So, it will have 4 roots. This means that all the 4 roots lie inside mod z equal to 2. Okay. Now, let us take mod z equal to 3 by 2. So, we will have to change now the choice of the functions fz and gz in order to show that one root lies inside the circle mod z equal to 3 by 2. Okay. So, let us take, let gz be equal to z to the power 4 plus 1, okay, fz be equal to 6z. Okay. Then what do we notice? Mod of gz is equal to is less than or equal to mod of z to the power 4 plus 1, which is equal to 3 by 2 raised to the power 4 plus 1, which is 81 by 16 plus 1, which is equal to 97 by 16. Okay. So, mod of gz, an estimate of mod of gz is 97 by 16 on mod of z equal to 3 by 2. And what about the function fz? Fz is 6z. So, mod of fz is equal to 6 times mod of z, which is equal to 6 into 3 by 2. So, this means 9. Okay. So, we can see that mod of gz is less than mod of fz on mod of z equal to 3 by 2. This means that gz and fz plus gz have same number of zeros inside C. So, fz and fz plus gz must have same number of zeros inside mod z equal to 3 by 2. Okay. Now, f z is equal to 6 z. Okay. F z equal to 6 z gives us f z has a 0, simple 0 at z equal to 0. Okay. Which lies inside mod z equal to 3 by 2. Okay. So, that is which lies inside in mod z equal to 3 by 2. Okay. So, f z plus g z, which is z to the power 4 plus 6 z plus 1 equal to 0, also has 1 0 inside mod z equal to 3 by 2. Okay. So, f z to the power 4 plus 6 z plus 1 equal to 0 has all the 4 roots inside mod z equal to 2, but out of those 4 only one root lies inside mod z equal to 3 by 2, because f z is equal to 6 z. So, f z has a simple 0 at z equal to 0 and z equal to 0 is a point inside mod z equal to 3 by 2. So, f z has a simple 0 at inside C, and therefore, f z plus g z, which is z to the power 4 plus 6 z plus 1 also has 1 0 inside mod z equal to 3 by 2. So, that is how we can decide the number of zeros inside the curve C using the Rouché's theorem. With that, I would like to end my lecture. Thank you very much for your attention.